All right, hello, hope you're doing well. This will be the last video for this chapter, and we'll cover just a couple problems and kind of mainly concepts in that we're going to compare real gases and ideal gases and cover some key points that you should keep in mind. So in this problem, we're going to calculate the pressure of a gas using the van der Waals equation, which I'll write down in a second. Another way this is referred to is by the name the real gas law. So kind of also write that here, real gas law. To compare, this would be where you would want to remember that an ideal gas, there's a couple of things we assume. So when we deal with the ideal gas law, we're assuming that these particles don't have any attractive forces between them, or what are sometimes called intermolecular forces, or repulsive forces, but you know, these attractive ones tend to be the more important ones. And also the particles don't take up space. Don't take up space. So the particles basically have no volume, right? Or negligible volume. And there are a couple other assumptions in the ideal gas theory. One is that the collisions are, you know, completely elastic. You don't lose energy, and then temperature is proportional to the average kinetic energy. But these are one of the ones that are the important ones, because when we're using the ideal gas law, which works pretty well, by the way, and by now we're all familiar with, we're just assuming these things are true, and for low pressures and kind of stuff like that, it works pretty well. But when we have a real gas, which we'll get into like with the next problem, kind of ways when it would not be ideal, there are these attractive forces that exist that just basically exist between any kind of particles or molecules. It's just a fact of chemistry and nature. And obviously the particles do have volume because they have some kind of mass. So that, you know, is true. And then we're going to use this formula that looks like this. So this is the van der Waals equation, or the real gas law. So you can put it on your information page, or you might see it on there if needed. This is supposed to be a B. Let's clear that up a little bit. And then you get, so what you get is a corrected form of the ideal gas law. It looks very similar with some other variables in here, namely A and a B, which you look up for different gases. For nitrogen, these are given here, A and B, but in the book they have a table for lots of common gases that you can use. Probably on Alex, I'm sure as well, they have all that data. So yeah, so we're just going to use this thing. I'll talk about these numbers, these A and B numbers, in the next problem, but basically plug them in. Everything else is the same, with pressure and N, you know, moles, and V is volume, and T is temperature, and the same value of R we're using with ideal gas law, 0.08. So we can, if I just kind of solve this for P, this is another way to write it if you want to rearrange it. Minus A over NV squared. So then I just kind of plugged in, oops, all the numbers. We have 1 mole. I'm not going to write down the units because we know the units are temperature in Kelvin, which was 40 Celsius, 313. 0.5 was the volume in liters, 1 mole. And then this, again, this B value, this thing is from given in the problem here. And then we're going to have an A value that's 1.39. So we're going to have 1.39 being that A value that's given, and then 1 over 0.5, this is squared. Okay. So I got 50.2 atmospheres. It's pretty high pressure relatively. I think if you do the ideal gas law, you get something that's like around 51 or 52. It's going to be higher than this. So the ideal pressure is going to be greater than the real pressure. That's true in these problems because of basically the attractive forces that exist in a real gas that kind of pull the molecules together and lessen the pressure on the walls of the container, right? One way I've heard to remember this concept is the ideal world is greater than the real world. You know, ideally we'd all get an A+ in chemistry with doing very minimal work, but it's just not how the real world works. So just kind of a sad fact, but nonetheless true, greater than the real world. Okay, so maybe one way to kind of remember what should come out with these numbers. And then the thing, like I said, why, you know, these would be number 11. I kind of just threw some problems to emphasize the concepts and things that you might want to keep in mind for these if you have concept questions. So one is when does a gas behave more ideally? And what you should remember is that this statement is false. So ideal is going to be the low pressure is true, but you want high temperature and low pressure. Okay. Under those conditions, what we find is what we said here, the no attractive forces and the particles don't take as much space compared to the volume of the container. This is also, if you think about it, conditions that lead to things being a gas. If you heat them up and you decrease the pressure, things tend to be in the gas phase, where if you were to cool them down and increase the pressure, they would tend to liquefy or form a solid, which obviously is not a gas, let alone an ideal gas. So, okay, another ways to think about it is in just the general states of matter, what is favored. B has to do with kinetic energy. Since I didn't have a specific problem about average kinetic energy, like calculating it, you can look at the formula, which is this one, and we generally just use the 3/2 RT, which doesn't have molar mass in it, it's just temperature. So this is true because if you have the same temperature, you have the same kinetic energy. So only depends on temperature. Okay, and remember it's the Kelvin temperature. So if they have the same temperature in Kelvin, and if you let's say you double the Kelvin temperature, you double the average kinetic energy. That doesn't work the same as if you double the Celsius. So if you double 10 degrees Celsius to 20 Celsius, that's not going to double the average kinetic energy. That's actually not a very big change in Kelvin. So just, again, things to keep in mind with temperature not being proportional in the Celsius and Kelvin units. We talked about this in the last problem, the intermolecular forces. This is false because it's the other way around, right? So we'd say real gases experience intermolecular forces, right? Or attractive forces. For D, there's a collision frequency problem, and this is this Z. So there's actually two Z equations, I think, in the textbook. One is the collisions with the wall. This is the collisions with the molecules themselves, which is generally the one that's looked at kind of more often. I don't know if on Alex, if they'll have you calculate it. Usually in terms of a test question, it's not that important to plug things in because there's some kind of funky units, like this D is kind of the diameter of the molecule, which you'd have to know. And then N is the number of molecules. So you'd have to do the moles times Avogadro's number. You don't want to use just N for moles there. Little n, it's different. So anyways, the important part is usually just the concept, like what would affect, the the collision rate. And I think with these ones, it's also more just common sense. You can kind of look at the formula. There's a lot of variables there, but if you think about just two gas samples and which one would have more of the molecules colliding per second or whatever unit of time you compare, then I would look at temperature, kind of average speed would be important. So temperature, these are both going to be the same temperature, and they're also going to be the same mass, which is 28 grams per mole. So same mass. So that's nice. Those things kind of just factor out of it. And then what we have is that one gas has a higher pressure than the other one. That's the idea, is that if you can just relate that to frequency of collisions, well, kind of by definition, the higher pressure means more collisions, at least with the walls of the container, which would also translate to more collisions with the particles themselves. So this should be true. The higher pressure is going to be a greater Z. Although in that formula, you won't see pressure, right? But you do see molecules per volume, which is related to pressure. So the higher pressure, you're going to have more particles per volume, which is in that formula. Okay, so that makes sense. And for the last one, this is again, van der Waals or real gas law question. And to kind of break that down into what these things mean. So A in that formula has to basically account for the attractive forces. And this is something that we get more into in Chem 1C with learning about intermolecular forces specifically, and what affects them and how to kind of compare different things. And for now, generally, like if it's bigger, it's going to have greater A, or if it's polar, it's going to have a bigger A value, which you may not know that much about polarity. That's fine. But water, for example, is a polar molecule. Again, we don't really cover this in Chem 1A, so it's not that important. But just to throw it out there. And then B is easier because this accounts for the size of the particles. So particle, remember, we assume that ideal particles don't take up space. This is a lot easier because then, again, if it's a bigger molecule or bigger atom, it's going to have a bigger B value. And you can just use the molar mass as a rough guideline for that. So we have helium, which is, one atom, which is small molar mass. Methane, CH4, which has 5 atoms and also a bigger molar mass. This would be, methane would have the bigger B value, and helium would have the lower or smaller B value. So this one should be false. And again, you can look those up if you're doing a book problem or Alex, but on an exam with limited time, I think just the concept would obviously be more effective at just saying, oh yeah, I know what that would be because it's bigger or that's smaller. Okay, well, let me know either in the forum or by email if you have any questions about these. You can obviously delve more into each of these topics and kind of expand on them. So I just wanted to hit them, at least on the surface, and cover what I thought were the main points, but let me know. I can always address your question in more detail by email. Okay, hopefully your studying goes well. Talk to you later.